Good day, everyone. I'm excited to share with you our presentation titled The Digital Catalysts, a review of optimization software in modern process engineering. This session explores how cutting edge software tools are transforming the way engineers design, monitor, and optimize industrial processes. There's a, this is a quick overview of what we'll cover today. First, we'll define what optimization really means in the engineering context. Then, we'll explore the motivation behind its adoption in process industries. We'll classify the types of optimization software and compare some of the most commonly used tools. After that, we'll examine how they integrate into engineering workflows, look at real world applications, discuss some challenges, and end with key takeaways and a chance for you to ask questions. Let's start simple. What is optimization? In engineering, optimization means improving a process by selecting the best possible option out of many. Think of it like trying to find the most efficient route to a destination using the least fuel, the shortest time, or the safest path. For us engineers, this could mean minimizing energy usage, maximizing yield, or reducing costs, and software helps us do all that quickly and accurately. Why is optimization becoming such a big deal? Well, industries today face increasing pressure to be more efficient, more sustainable, and more profitable. Traditional trial and error methods are no longer enough, they are too slow and unreliable. Optimization software allows us to model, simulate, and improve processes virtually. It helps engineers make smart decisions before anything physical is built, saving both money and time. So, what are we trying to achieve with this review? First, we aim to understand the different types of optimization software and what they are designed to do. Then we'll look at their key functions and limitations. We'll also explore how these tools are applied in both research and real industries. And finally, we'll give some suggestions for how engineers and organizations can best adopt and benefit from these tools. Now that we understand the need, let's move on to how optimization is categorized. We'll keep it simple and go through three major types. First up, simulation-based tools like Aspen Plus and ChemCAD. These allow you to create models of real-life processes like distillation columns or reactors and test different conditions to see what works best. Second, mathematical solvers such as MATLAB and GAMs. These are more equation heavy. They are excellent when you are dealing with systems of constraints or optimization equations. For example, GMS is often used in logistics and supply chain problems. Third, hybrid systems. These combine the modeling capabilities of simulation tools with the mathematical rigor of solvers. This hybrid approach gives more flexibility and can handle complex real-world problems better. Let's do a side-by-side comparison to see what sets these tools apart. Aspen Plus, ideal for chemical process simulation, used widely in oil and gas, strong on thermodynamics and heat or mass transfer modeling. GAMs, best for large-scale optimization problems involving multiple variables and constraints, perfect for resource allocation and energy planning. MATLAB, highly flexible and supports custom algorithm development. Great for control systems, heat exchange design, and predictive modeling. ChemCAD, similar to Aspen but more user-friendly, great for education and pharmaceuticals. Now, how do these tools actually fit into engineering workflows? Optimization software plays a role at every stage, from early design to daily operations. Engineers can simulate plant operations, test different input scenarios, reduce waste, and even forecast failures. Also, when tools are integrated, say Aspen with MATLAB, you get both depth and flexibility. This means better design decisions, quicker troubleshooting, and a more adaptive process overall. Of course, it's not all smooth sailing. Here are some challenges and limitations it faces. Cost. These software packages can be expensive, especially for small organizations. Learning curve. You often need advanced training to use them effectively. Data dependency. The output is only as good as the data you feed into it. Integration. Combining different platforms, especially across departments, can be technically challenging. And finally, organizational resistance. Some people still prefer the old ways. Let's look at some real life success stories. Petrochemicals. In one project, Aspen Plus was used to optimize a distillation unit, cutting energy used by 15%. That's a huge saving on operation costs. Pharmaceuticals. GMS was used to improve batch scheduling, resulting in faster production cycles and higher throughput. Food industry. MATLAB models helped optimize heat exchanger networks, reducing energy consumption and improving product consistency. Sum it all up, optimization software is no longer a luxury, it's a necessity in modern process engineering. It helps improve design, boost efficiency, saves energy, and supports sustainability. By combining simulation, data analysis, and smart algorithms, engineers can make faster and better decisions, something that's absolutely vital in today's competitive industrial landscape. That brings us to the end of our talk. I'd love to hear your thoughts or answer any questions you might have. Feel free to ask anything, whether it's about specific tools, applications, or future trends. Thank you so much for your attention. This presentation was put together by Opon Kwabena, Udumsonia, and Kusifin. We hope it's inspired you to think more critically and creatively about how software can enhance engineering processes.